GothamQ. So let me just make sure that yes. So Qunnect built this network called GothamQ in New York City. It's a test bed for trying to prove out our technologies. We are a quantum networking company. We build hardware that supports generating entanglement, distributing entanglement, preserving entanglement, and all of this is en route to actually building the quantum repeaters, which you heard a little bit earlier was one of the great goals of trying to extend distances. But when they invited me to give the talk here today, they wanted me to talk about the use case study of, like, why would anybody want to distribute entanglement over existing telecom fiber? And that's exactly what we're doing. So let me just go back actually on this one. The map, the satellite map you see on the side, that is Manhattan on the left and Brooklyn and Queens just below. Qunnect sits on the border of the two, next to the East River. We have a 34-kilometer segment of fiber that has 6 fibers in it that runs through Brooklyn and Queens, and then we have another 16-kilometer segment that runs to 2 different NYU campuses. Sorry, back this way. Yes, the lights are actually tough. Yeah, sorry, what everybody else has been talking about. Right, anyway, the sort of news in all of this is that this network went live in April of 2023 with our equipment supporting it. We had a live tour recently in October during one of the IQT NYC conference where we showed people what we were doing. And now this network is real. So it becomes both a test bed for us in order to be able to improve the designs of what we do, but also in order to start proving out use cases. And when we start thinking about quantum networking, again, there have been several talks that preceded mine that are talking about different flavors of quantum networking. I think these are sort of the 4 main candidates that are out there right now in terms of different things in the technology space. PQC, which you heard quite a bit about earlier, is, of course, the algorithms which are intended to be quantum resilient in the post-quantum crypto world, championed by NIST. What's nice about them is they run on existing commercial equipment and, of course, offer an improvement over the cryptography solutions that we have now. Then also what has been mentioned quite a bit today is the sort of next step up, and that's the first step into physically protecting classical information, and it's by actually transmitting it over quantum protocols and quantum key distribution. While the US has not been supportive of this in terms of championing it as an in-use technology, the EU and China have been supporting it quite a bit. China has an existing network. The EU has a commitment in order to build QKD networks across all of the existing member states. And then there are these 2 other flavors, which is where Qunnect actually works with most of our technologies, and that's in the latter 2. So one idea is that if you can actually generate and distribute entanglement well, maybe you could use it simply as a physical security layer to either augment the protection of the existing digital network streams or of the digital topologies. And it was hinted in one of the previous panels of that type of use case. And then the final vision, which many people refer to as the quantum internet, is this idea that if you can distribute entanglement well, maybe you could also push beyond secure communications as a limiting application and go towards things like distributed computing and distributed sensing. Those latter 2 applications have been, the latter 2 types of networking have been supported both by DARPA, which had a recent BAA call on the augmentation front, and then also by the DOE, who has been championing the quantum internet for the last few years. So if you would like to distribute entanglement, there's a number of design challenges if you're trying to do this on existing telco-grade fiber. So the first one is that if you ask people in, let's say, New York City to give you some dark fiber, it's fiber that has been laid ever since the mid-'80s. So you have no idea when you ask them, I need a loop of a certain size. I don't care where it runs. I just need it sewed together. It has to be dark. You have no idea how good the quality of the splices are going to be, nor the quality of the existing fiber because of the decade it was laid. So we had no idea when we actually got this network together what we were going to see. So that was obviously a big wild card. Qunnect chooses to work with polarization qubits. Some of you are kind of familiar with the standard types of qubits which are used in the quantum computing world and the communications world. The 2 major types of qubits are time-bin qubits and polarization qubits. Time-bin qubits are rather easy to create, more often than not using a Mach-Zehnder interferometer. However, polarization qubits are things which are a little bit more native to quantum computing and quantum sensing and other types of physical processes. They are also native to Qunnect's quantum memories, which again are part of our larger repeater suite. So we use polarization qubits as our means of transmission, but the problem is that if you send single photons with given polarizations down long fibers, the fibers themselves actually cause rotation and polarization drift of your qubits, which results in problems in fidelity. So you need to be able to correct for those. So they traditionally were not used as communication qubits because of that, or at least over long distances. We have instruments to correct for it now to make it possible. Then also, the entanglement source, which actually generates the photons which you'd like to distribute, has to be giving you extremely high quality qubits and at rates that start to look like things that you would want to actually be able to use for communications. I think we all know the garbage in, garbage out idea, right? So if you're already putting something in that has a large amount of error and bad fidelity, it's not going to be better after you transmit it through 35 kilometers of fiber. And the rates themselves have to start to be of the level where you can actually encourage adoption. So I think use cases, it was pointed out in one of the panels this afternoon, that in the case that the rates are 1 key per day, it's not going to be something that people are actually going to try to adopt and use. If you are going to decide to distribute entanglement, of course, you're going to have to learn how to preserve it. So if you don't have low quantum bit error rates, again, you won't be able to tell the difference between an eavesdropper who is on your line or the fact that a subway passed by your fiber bundle. So the added security of quantum is basically useless if you can't maintain the fidelity. And finally, networks have to maintain uptime. There's no way that we can actually start thinking about a quantum network being useful if the uptime is like 5%. And again, in one of the previous panels, we were talking about Messias, the satellite. Of course, it was a great technological feat that this was launched, and you can use it as, again, a broadcasting entanglement source that's in orbit. The problem is the visibility window when it passes over, right, of course, is quite slow. The data for the papers that we all refer to whenever we talk about the data that came from those experiments, right, was taken over the period of like 6 months in order to collect enough statistics to have something to actually report. So the instruments which Qunnect has built have been a little bit of a labor of love. We've been together in the Navy Yard working on these instruments since September of 2020. So we're a few years into it now. We do the basic research, which is at the tabletop level. We learn what we need in order to have the performance specs we want. We then put it into a box, and then those boxes eventually become rack units. So the format that you see there for our entanglement source is something that is 1/3 of a 2U rack. The polarization compensation device you see in the center is a 2U rack box, which is a little on the shorter side. And then finally, the locking device is an atomic reference, which stabilizes the entanglement source. Is actually being packaged now in our laser product, which is something that we started building because of some supply chain issues. So the source itself is the only sub-gigahertz line width source on the market. It operates routinely at 10 million pairs per second. We can push it up to about 80 million pairs per second. It produces extremely pure HH plus VV pairs, which means, again, these highly pure, high fidelity pairs are what's necessary in order to make sure what you actually put in to the fiber is good. If you want to maintain it, you need to have something which is going to fight that polarization drift I was talking about. So our second instrument, this autopolarization compensator, is a little bit like a set of noise-canceling headphones. It sits on either end of a fiber, which you would like to use for quantum communications, and performs a time multiplex protocol where it samples the fidelity of the fiber itself by sending a series of different polarization pulses. The receiver box compares it to what it should have received, and then it calculates a compensation signal, which is then applied to every quantum signal you send when it goes back to quantum transmission. Those two devices together are really something that we're very proud of. I'll show you the rates in a moment. But they allow us to have the types of performance that start to look like, again, real networking. And then finally, the lock is an interesting thing. We all know that quantum has had a lot of success with atomic clocks. This is the same sort of concept. So Qunnect uses atomic-based devices. We use the lock device, which has an atomic vapor cell in it, in order to very accurately lock our wavelengths that pump the source in this incredibly inexpensive way to be able to put something in every single node of the network that you could use for the same very tight reference. So the protocol we're running right now on GothamQ at least the one I'll share the data for, is that the noise canceling headphones, or APC, samples the line every 20 seconds. It compares the fidelity, which is measured, to a threshold, which you've determined in our software. Whenever it drops below the threshold, it runs a compensation cycle. If it's above the threshold, then what it does is it goes on and it basically checks the line for the quality of the entangled pairs that come back to the detectors. So are the pairs still entangled? So it runs a CHSH measurement. And what is the real-time quantum bit error rate? And the numbers that we get are presented here. So the two segments, the left-hand column is the Brooklyn-Queens loop. So those are 34 kilometers with about 17 dB loss on the fibers themselves. The rightmost column is the NYU section, which is the 16-kilometer piece between us and Manhattan, with about 10 dB loss. That actually has a submarine segment that runs under the East River. So on the Brooklyn and Queens loops, we are actually able to inject a few million pairs per second and recover 130,000 pairs per second of exceptionally high quality entanglement. So that's the 2.7 S value there, with qubers of less than 2.5%, running with 99% network uptime. These numbers have never been shown by any other system at those high rates and high qualities. More importantly, this is just running with 95% channel fidelity. We can up the channel fidelity now with some of the improvements we've made in the algorithms and actually run it with the same specs. These were all measured using nanowire detectors, which you heard the ID Quantique talk earlier. So we use cryogenic detectors when we're running on our loops in order to have the best detectors out there for being able to see small events. But then we wanted to say, what could you do with SPADs if you go to another remote detection place? So NYU doesn't have a nanowire. So what we did is we took some of our portable 2U racks that have some telecom SPADs in them from Aurea. We put them on the other side of the NYU line, and then we ran the exact same experiment. And you can see the numbers are very comparable except for the rate. So one challenge with using the non-cryogenic detectors, which are available right now, is that you have to gate them. So you artificially suppress your rate because you have to gate with anticipation of what your counts will be. So it runs about 10-fold less, but that's not terrible because you're still getting all of the similar performance specs. And to put this into context, Qunnect's numbers are in the lowest level of the table there. These are all of the known published examples of distributing polarization qubits over long distances in fiber, and the MISSIA satellite experiment is at the top row. So what you can see in the center there, the coincidence rate of 130,000 counts per second, right, or pairs per second that are being distributed, compared to every other experiment before it, is like night and day. And now you're really starting to talk about things where you can actually start thinking about doing the communications protocols that we're all thinking about in terms of use cases. Moreover, we're running 99% uptime for over 7 days at a time when we turn it on. And all of this is due to the fact that something that is seemingly simple, which is this auto-calibration of the fiber to continuously maintain the fidelity, allows us to stay in a regime where we're constantly broadcasting and correcting, right, without having a lot of drift. For all of these other experiments, because they were academic proof of concepts, they calibrated the system, they ran their experiments until the system went out of Qber. So in most cases, they were using Qber as their metric. So whenever the error rate got too big, the experiment was over. They didn't have a system for compensating for it. So that's seemingly like a simple solution, but it's just an example about how quantum support instruments sometimes enable quantum to happen. And of course, we are working at over 100 kilohertz. So this means that we're like at least twice 56K now, right? So, we're getting there, right? Okay. I'd like to also make the case for atoms. We work in rubidium, which of course is used in plenty of quantum clocks, just like cesium. What's nice about them is they're naturally like a really great way to have really high precision for not only timing, which we use in the clocks, right, and position, which we use in the PNT applications, but wavelength. So it's an inexpensive way to distribute things across large distances, or at least as a reference standard. We also use them because you can generate our photons with them, you can stabilize them with the clock and a reference signal, and then you can also capture them with our memories, which are also using rubidium vapor. So what we started off as is a quantum company that had both warm atom sort of dreams of being able to build these quantum memories and the realistic expectations that because we work in warm atom systems, we'd like to be compatible with cold atom systems. Warm atom systems have to be sort of like, I mean, not surprisingly, there's a compromise. So warm atom systems don't have the same coherence time as cold atom systems. So what's nice is if they're all using the same atoms, you'd be able to create these hybrid systems for long-range networks. To give you an idea who's out there in the space, Qunnect, obviously in the center, has products within several different regimes. I would make the argument that the more near-term commercial use case is on the left-hand side. This is the idea of just distributing entanglement over shorter distances without repeating. For that, you need entanglement sources. There's a number of SBDC sources on the market that utilize crystals. Those are all fine for doing communications work, but they're not good for scaling into things where you need to actually interface with other quantum devices. The problem is the line width of things which come from those SBDC sources is typically in the terahertz regime. And many of the atomic things which are on this chart require hundreds of millihertz or so in line width in order to have useful intake of the photons from matched line widths and low losses. We, as a company, have decided that it's important to work on all of these support devices on the bottom, the software in order to be able to support the control of different instruments, the precision references in order to be able to put these things in a multi-node system. And we're hoping that having both the entanglement sources and the control systems and the references and the support instruments will allow us to more easily move into the repeater world where quantum memories are key. There's a number of different memory technologies out there. The only room temperature operating memories are ours, to our knowledge. And as we see everything evolving towards long distance applications, we of course will need to bring repeaters online. So Qunnect really thinks very similar to what you've heard in some of these other talks today, that it's important to learn what you can at short distance networks and then go to long distance networks. So if you can start building short distance networks that are enabled in the high security space, like for finance and defense and critical infrastructure, you can then make the case that it's worthwhile to connect them using repeater technologies. That's exactly how our product line is going to evolve. So right now, we commercially sell 4 of the products on this chart: the source, the lock, the memory, and the APC units. In order to make this a cohesive set which is available for a drop-in solution to somebody who wants to start doing this type of research, we realize we have to now start building a laser product. So by the end of this year, we'll have that out as well. We also have a timing and a validation piece of hardware which allows you to actually perform these protocols to do something similar to entanglement-based QKD, which we anticipate will be done by the end of this coming year. And in the background, we've been evolving our memory products to go more broadband while our source is already quite narrow. And the entire idea of that is to minimize the loss between those instruments in order to be able to support actual repeating protocols. Who are the market for all of these things? Well, arguably everybody who's using anything that they buy from us right now is a quantum network researcher. This is where the market is today. The requirements for this, of course, is that you have a laboratory with other types of support equipment in it, and you have people within that laboratory which have some basic knowledge of AMO physics or quantum optics or both. We sell our products, which we would call research grade, into that market right now. So our Metro Mini bundle and our Metro bundles are intended for that market. We want to evolve our products so that we can actually give these to network researchers. And of course, the difference between that is these things should sit in server racks. They should be completely software driven. And we started thinking of this product not only as industry grade, but basically quantum inside. And I think that's where the industry is really going to see a turning point when we sort of no longer have to have somebody understand the quantum, but they can use the quantum in a more sort of blinded physical sense. So this is the team. We just hired our 18th employee, so we're very proud of this. They work really hard and have done amazing things in a few years, and these are our facilities. So we have a 4,000 square foot research facility in the Navy Yard and another 1,500 square foot network research hub where we invite people to come and test use cases using our equipment. Thank you.
Great, thank you, Noel. We have time for one quick question, if there are any.
Must.
Yeah.
Okay.
Just two quick ones, actually. The wavelength of your entangled source, 1550, 800?
We're actually working in the O band,
Okay.
so we work at 1324.
Okay.
It's actually a bichromatic source, so it's a bit of an oddity. We use spontaneous four-wave mixing in order to do it. So one photon's at 795 and one's at 1324.
Okay, so it's four-way. Do you still get double pair emissions at some point once you push them hard enough?
We haven't really. So there's an archive paper out on the source that fully characterizes it. We actually were surprised that we could push it as hard. I mean, I know you're asking this because of the millions per second problem, right? So in the SBDC world, of course, this is a very common phenomenon, but in our particular source, we actually haven't seen it. So the bunching rate is extremely low. The natural line width is in the kind of 500 to 700-ish megahertz. You can tune it. You can tune it a little less than that too if you want to take it down to 300. Our broadband memory is at 300 now, so we do that sometimes in order to do the matching experiments. But yeah, it's an interestingly simple piece of optics in order to create something which is more compatible with the other types of atomic things you might want to couple to.